Hello! In this video, we are going to prove the following theorem. Let m, n, and p be integers, where m is less than or equal to n, which is less than p. Then, for all lists of real numbers, am through ap, the sum from I equals m to p of ai is equal to the sum from I equals m to n of ai plus the sum from I equals n plus 1 to p of ai. Right, so this theorem is essentially telling us how we can take our sum and break it up into individual sums. Right, so now let's get into the proof. And to start out our proof, we will start out by giving ourselves arbitrary integers m and n, where m is less than or equal to n. And now we're going to proceed by induction on p to show that for all integers p greater than n, that this is true. Okay, so let's start with the base case. In the base case, we're trying to prove that this is true in the case where p is the smallest integer greater than n, which means we're trying to prove that this is true in the case where p is equal to n plus 1. So really, we're trying to prove that for all lists of real numbers, am through an plus 1, that this is true in the case where p is equal to n plus 1. So we're trying to prove the same about all lists of numbers from an to an plus 1. So give me an arbitrary list of real numbers from an to an plus 1. And our goal is to prove that this is true where p is equal to n plus 1. So let me start out by writing the left-hand side. To start, we know that n plus 1 is strictly greater than n, which means we can take the n plus 1th term of this sum and pull it out from the rest of the sum, which means we can rewrite this as the sum from I equals m to n of ai plus an plus 1. However, we know that an plus 1 is the same thing as the sum from I equals n plus 1 to n plus 1 of ai. Right, because whenever the lower and upper bounds of a sum are the same, we just take wherever you see an I and replace it with n plus 1. And that's what we have here. So as you can see, we have shown that this is equal to this, which means we have shown that this is true in the case where p is equal to n plus 1. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer p greater than n and assume that this is true. The whole goal of the induction step now is to prove that this is also true for p plus 1. So really, we're trying to prove for all lists of real numbers, am to ap plus 1, that this is true where instead of p, we have p plus 1. So give me an arbitrary list of real numbers from an to ap plus 1. The whole goal is to prove that this is true where instead of p, we have p plus 1. So let me rewrite the left-hand side where we have p plus 1 here. Now, since p plus 1 is strictly bigger than m, we can pull away the p plus 1th term of this sum. And so we can rewrite this as the sum from I equals m to p of ai plus ap plus 1. Now, we would like to rewrite this sum as this sum plus this sum. And we're actually allowed to do that, right? Because to use our induction hypothesis, we need to have a list of numbers from an to p. Well, we have a list of numbers from am to p, right? That's exactly what this list is. So taking our list of real numbers from am to ap, we have that this is true. So we can substitute this sum for this sum plus this sum. But now notice, we know that ap plus 1 is the p plus 1th term of this sum. So really, we can rewrite this as the sum from I equals n plus 1 to p plus 1 of ai. So notice, we have shown that this is equal to this. And so, what that means is we've shown that this is true, where instead of p, we have p plus 1. And that was the whole goal of the induction step, so this completes the induction step. And since we've done both the base case and the induction step, this closes the induction, which means we have proven for all integers p greater than n, we have that this is true. Well, since m and n were arbitrary integers that satisfy this condition, this means for all integers m and n which satisfy this condition, we have for all integers p which satisfy this condition, that this is true, which means we have proven the theorem. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.